Não, grava tudo. Eu vou ter que falar em francês e inglês de francês. Ô, professor, como vai você? Ah, no samba. Tudo bem? Você tem mensagem? Sim. Nossa, professor, ele é physicist.
Ok.
Personne n'est parfait.
Tá dando aí o som? Tá bom? Então, meus caros, prazer estar aqui apresentando um grande amigo, um grande colega em português. Depois vou falar em inglês. Então, é um prazer também estar aqui apresentando como se eu fosse membro aqui do LSBD, mas agora que eu tenho minha credencial devidamente registrada, me considero parte do grupo. Então, para todos que estão também vendo depois ou agora online na transmissão, então, é verdade, né? Então, isso fica gravado. Gente, um prazer, então, apresentar um colega, um amigo, Vincent Oria, meu colega de doutorado, lá se vão mais de 30 anos, que a gente se conheceu na França, na Télécom de Paris, né? A gente dividia a sala, a gente trabalhou na área de banco de dados, tivemos o mesmo orientador de doutorado e convivemos bastante. A gente até hoje tem uma amizade muito grande. A gente não trabalha nas mesmas áreas, a gente não colabora muito mais, mas a gente tem um contato muito forte. Então, o Vincent fez um percurso francês de formação, mas ele depois rodou o mundo, da origem da Costa do Marfim, mas foi para a França, depois foi parar no Canadá, trabalhou com um colega nosso, Mário Nascimento, lá em Alberta, e hoje ele está em New Jersey, no NJIT, New Jersey Institute of Technology. Neste momento, já faz algum tempo, ele é o chefe do departamento lá. Tá? Então, ele vai falar para a gente sobre análise de dados solares. Estamos todos curiosos, eu também. Então, vou falar só uma palavrinha em inglês, só para ele saber do que a gente está falando. So, welcome, Vincent Oria. So, it's a colleague. He works for NJIT. He's a department chief. If you stay this,
Yes.
from this to there, you're
Yes.
gonna be
Okay.
over the world.
Okay.
On the camera. Right?
So
it's
everybody can see you.
It's a great friend, a great researcher, has got so many prizes too. He's well known from the database community, very many places. It's a friend and very nice person too. You enjoy, I'm sure, his presentation. Mr. Vincent Vicentinho.
Obrigado.
Before you start, you have about an hour or
Okay.
so,
Yeah, that's fine.
and then we, at the end or during your presentation, we can.
Yeah, you can ask
it's
questions.
it's up to you.
Yeah, no, you can ask question anytime, so it's fine.
Okay, thank you.
Okay.
Go ahead.
Thank you for the invitation. Thank you for having me here. It's the first time to Fortaleza, but I'm sure it won't be the last time. So, I'll try to give justice to what we're doing. I am from the database community, and now everybody is moving toward. Well, I'm not a machine learner, but everybody's using some kind of machine learning, and to do some kind of analysis, you need data. Now, why did we start this project mainly with the physics department? Well, there is a reason why the term astronomic is used everywhere, because even in there they have in astronomy, the data is also astronomic. So they have a lot of data, and so maybe by using machine learning and combine that with the wisdom of the community in forecasting this kind of event, and we'll talk about them a bit later. So I'm working with Alexander Kozovichev, Sasha, as we call him, Jelu, Slava, who was a former student of Alexander, but he's now at Georgia State. So these are some work that we're doing with them and some of our students. Okay. So this is a big topic, so I'll touch about two parts of what we did. So we use machine learning just to do some kind of data compression or feature selection. So that is the first part. And second, we try to see if we can predict some SAP, so solar energetic particle event forecasting. I'll talk a bit more about that a bit later. Now, this gives, we try to study the sun, but, well, nobody can even go close. So there are some spacecraft that are sent, and also some base station that observed the sun. And so here you have some kind of, so all these instruments collect some data. And here, these are in petabyte of data. In the expected lifetime of each of these observers or spacecraft. So if we take, for example, look at the data scale here, the measurement. The SDO, that was launched in 2010, is sending about 5 terabytes of data per day to the Earth. So, and then you have all of these. Now you want, so the main issue is how to use this and how to make sense of this, of this type of data.
I have already a question.
Yes.
So how complex is this data? It's just how a very large flew of the same kind of data, small.
They have different type of data, but mostly they try to observe. They have some waves. So the magnetic waves that we have there, and so this kind of data that they want to observe, but they can be, they can have different, the same event can be observed by different instruments, and then the data can be a bit different. So what we did was also to do some kind of data integration and cleaning before we were able to start working on this.
But mainly this is a very not complicated. I mean, the type of the data is not very complicated. Just a bunch of numbers of the same kind.
It can have numbers, but these are you have data in high dimensional spaces basically. Okay, so yeah. Okay, so what we want to do is use some kind of algorithm on that. Machine learning is not magic. So basically, we use the past, which is the data that we have, to predict the future or try to use that. This may work, but what we want to do is use machine learning techniques and also combine them with what the physicists were doing and see if that can yield better results. Now, this was from 2022. That was just to show the penetration of machine learning in the community of the physics community here. So these are the papers that are published. So the blue are referred papers, and the green are not referred, but these are basically gives an idea of the number of papers. But that at the same time, look at, so here the number of machine learning papers that are being used, that, you know, so the same type, same data here, but these are the papers that are based on some kind of machine learning. Okay, so you can see that it's growing, and just because, you know, with all this data, it's difficult to be able to analyze it manually, them manually. So
And again, mostly like doing prediction, right?
You can do prediction, even augmentation of the data, because you have some values that we get. You want to be able to add some to it. So it's, well, I'll talk a bit about what we're trying to do here. Well, we want to enhance some space weather, so do the forecasting.
Okay.
First, even do some kind of object recognition and classification type. So you have some events. What I did this event there? We can use that to also enhance some physics-based model that was the model that we're using before, and do some exploration of and discovery on large dimensional data that we want to use there. Try to come up with, maybe they have some problem that are specific to them, and define some specific algorithm to be able to treat the problem that they may have. So I'll try to talk about the first work, the spectropic line compression. They're using autoencoder. Now, before going any further, let's try to see if I can, can talk about that. So,
Okay.
This is the sun, okay? And what we observe is a tiny part here, and even that, we have different layers, the photosphere, the chromosphere, and the corona here. And that's where you have all the activities. So that's the only part that are really observed. The rest of the sun is not really observed. Okay, so and then for this part, using different wavelengths, you can get an idea of what is going on in this part of the sun. Okay, so just using different wavelengths, you can collect some type of data. So that's what most of the instruments are doing. Now, this is when you measure all these waves, there you get this spectrograph that is sent by the machine that are sent there to observe. And if we take from just April 20, 2021, 8 p.m. to 9:56 p.m., we get about 300,000 individual magnogram. How can you represent that, and how can you compress it? So that was what we're trying to do here for this data set. Okay, so what we used was an autoencoder. So this is a typical machine learning. So you have your input here, and here you define how many dimensions you want to get. So, and then you try to see from this dimension if you can recreate what you observe here to see if the representation is good. So the study was to see when can we stop. Okay, so we start until we get something that can be a good compact representation, but if we can also interpret it from the physics point of view, that would be more interesting. Okay, so we go back here. This is the number that we want to have. So what we did was we varied this number to see, so we have 110 dimensions at input, and we try to vary it, and then we check to see the accuracy, or measure and see when can we stop. Okay, so
I have another question.
Yes.
I'm sorry, I have
No,
so
that's-
many
that's
questions
fine.
because I don't know anything about that. So this is why I have so many questions. So what's the quality of the data that comes in?
But these are just the data is that's what we observe. So these are the lines that you have there, the weight. So these are the data. So they are the only thing that we had. I think we have two. We get data from two sources. One is getting just one observation, and the other one has different observations. So we were trying to compile the average, but yeah, the data is not a problem. So
Okay.
we didn't do most of the cleaning is to align the data that we get from
All
different
right.
sources.
Okay. I see. Yeah.
Okay, so these are different lines that we have the original line, and then we're trying to see if we can, when we do the reconstruction, how accurate it is, and we superimpose these two. So that shows that the result was good. And here we try to see the reconstruction error, and that's where we can see where to stop in the number of, so if the errors is getting stable, then you don't need to compress any further. So when we did that, one can see here from 110, we were able to compress it to 4 already. After 4, the change wasn't that much. So, for 110 to 4 was good. Okay. And then the next thing was that how can we interpret that, the 4 dimensions that we got? Are they meaningful from the physics point of view? Okay. What are they about? And what we did was we compute some kind of variation. So this is the mean, and we have some variation. We vary the data a bit, and then we have that the input. Okay, for each of these 4 dimensions, and try to see what if it can be interpreted. So dimension 3, for example, when you look at it, when you plot several times, it seems to be responsible for the line profile asymmetry that we have there. The dimension 4 control The feature depth can different. You can see that it varies there. So each of these dimensions can be interpreted. So, but that came as a bonus because we were just trying to compress the data, but then see if it can be interpretable, and that was, that was a good surprise that we had there. So, just using the first study here, we just use just for some compression, and we're able to take some data that we have for 110 dimensions and compress them into 4 dimensions, and that was able to make sense of it. Okay. Now we'll talk a bit about any question on the first part. That was yes.
Just a comment. Maybe it's important to know. I think it's important to note, actually, that before activating any machine learning program or application, it's very important to deal with the data before whatever you get inside and outside. If you don't work, I see so far you were working actually just to be sure you have a good quality on the data so you can continue and be doing this. And I think for all people for everyone that works in the database area, this is so clear that is important, but it's not clear for everybody. So people think, oh, just take, machine learning, they will adapt to whatever you have. Don't worry, it's not true. So you get sausage inside, you get sausage outside. Just to be clear what I'm talking about.
Yeah. And I'll talk a bit about this data cleaning part in this second part of the work of it. Thanks for the comment. Yes.
Okay, hi. You mentioned, I'm speaking here. Okay. So I just want to know a little bit more about how you came with 4 dimensions.
Okay.
There is a part that in the slide.
Go back.
Not.
Okay. That's yeah. So that's what I mentioned that a bit here. So when we have it, what we want is this is unknown. So we just said let's see how many dimensions we can have. So the way we did that, we took 110. We took 1 dimension, 2, 3, 4, and then we did this. And then we were recording the accuracy all the way to 14, and then we continue. But then you can see the error here. And from this curve, we didn't gain much going any further. So that's how we stop. So we run it several times, and then
So the elbow rule, the method is the elbow.
So we didn't know how many dimensions we can have, but we were trying to see, like, running it and then see,
Your main goal at this task was to compress the data, right?
Because we have a lot of data. This is the data at 110 dimensions. If we can, so each of these 110 dimensions, store it with 4 dimensions, it takes less space and it is easier to work with. Okay.
Each dimension, it's a line?
What we had before was the line that I have here. Each dimension was this line, but that was 110 points. Actually.
Okay. Thanks.
Yeah. Yes.
Here in the ELSPD, we worked in a project that is just to try to figure out about the audio that works like a spectrogram. Mm-hmm. And we tried to reduce the dimension just with a CNN, a convolutional neural network. Mm-hmm. And I want to know if you tried something different like a CNNs or like a transform to make this embedding and this latent space.
You just want to find the good embeddings.
Yeah.
So before we were doing feature selections, like try to engineer which feature to select. But now we have a ways of, so we can, different methods that we can use. So we try this using the auto encoder, just because to see, but we can use some other method. We have not done with some other method, but we can use some other method, yes.
I'm just trying to understand whenever you're trying to find out whenever you're trying to find out this optimal value, do you do it empirically? Do you do tests and you find out whenever the error stabilizes, or do you apply like a PCA, or you do
the passengers and all this will be less exposed? So, but that's what we have there. So you have the solar flares. So when you have the flares, you have what the coronal mass ejection, which are particles that come there, and then you have the solar energetical particles that can travel through the space, and that's what we want to be able to predict. So the sun and the earth are not isolated. There are some kind of interaction, and they interact both during extreme event and at some scale. These interactions are called solar terrestrial interaction or space weather, and it is people think that the space weather have some influence on the weather we have on Earth, although it is not used for to forecast our weather correctly. So, as I said, the solar energetical particle can damage spacecraft electronics when that happens. You have more radiation exposure, and so they represent a potential danger for space exploration. Okay, and so these are the same thing that we're talking about. When you have this exposure, what can happen to now these you have different activities on the sun, call it the cycles. So the activities are not the same every time. So there are some cycles. So this is the solar cycle 24. There are some names there, and I can show you. So that shows a bit of activities that we have in different type of cycles of the sun. And here, that is from 1960. So when I talk about the cyclic activity of the sun, so sometimes it's more, can go down a bit, and then you have there, so it's cyclic. And this is something that we want to predict. And then also, if you want to send people in the space, you don't send them when you are at the peak. They are more exposed. But because this study, we didn't know much, well, the people didn't know much about this. This was where, when you take it, where they have the Apollo mission. So it was at high activity. Luckily, they all came back and they live long lives, but it was a dangerous operation. Okay, so, and then we're still having, currently we are having some high activities there. So in this cycle that started there. Okay, so yeah, so that was what I said before. The when they were doing the Apollo mission, it was yes. So but this was learned afterward. But it was really a dangerous operation. Anyway, so that's why we want to be able to predict it and be able to see what we can do with it. So what we're trying to do, we have some observations. So all these solar energetic packages, solar flares that we have there. And then, so either you can use the observations, use some physics-based modeling, that what they were doing before, and do the forecasting, or just use the data and do the forecasting by just using pure machine learning. Or what we try to do is something in between and try to merge, what we can do with both of them here. Okay, so so that is the project we're doing. So again, these are the same collaborator. These are the students who help us working on it. So the first thing was to get all the data we have from different sources and try to integrate them. Now, for that, we are using simple database integration, but at least knowing that, when you have an ID here, this ID corresponds to, so basically these are the same event. It's not easy because you have to maybe use the properties to match there. So to do this kind of integration. So we will use machine learning. We want to use, we want to integrate the data, the database. At least have the data in one place so that we can do the, and then maybe augment the data because some of we can compute some properties that add to the data that may take time to compute. So we do data augmentation, and all of these were stored so that we can use that to do the forecasting a bit later. Okay, so that project was supported by NASA, and that was, this was, we have this, this is the portal that we have there. We can have the different data sources. And then, as I said, we did some kind of integration. And hopefully this still, it's working. And that was, we had this interface there, this whole system, implemented on the NASA portal that was there. So that was a picture for the NASA portal there. So what we did was the data integration. So we took the data from different sources, and we take what we call space weather event. Can be SAP, can be so what type of event that we can have, and then how these events were observed. So we have the observation, and then we have so we define the schema, so and then we get the data. We integrated all the data from different sources, and we have that here. And then from that, you can visualize the data. You can query to see, you want to have some solar flares that happen there. So we know the start time, the end time. And then this is a visualization tool that we have there that can tell you, that can show you the evolution of the flare. So that's from the first part of the data. So we can just do data integration and have it in one portal where you can query, based on the properties, based on dates, and then you can be able to do the integration there.
Okay, I have a question. I guess
Timing was a big problem in there
Yes.
because events. To know how an event, it's the same event that is collected from another appliance or another, have to have, the same event time.
Yeah.
Right?
So here, time was, but they are not recorded at the, there can be a bit of shift. But yes, time is, because and all this data are about flares. So we know if you see some activities, you can see, well, these two maybe you see the time, the date a bit.
Right, yes.
And you can try to merge them, see they're about the same.
Right, but they arrive here. You can observe them in different, it's not the same. There are different distance, right? So they
are
get
different
here.
Yes, so that's why I'm saying there can be some shift in time.
Right.
Yes, so but you don't have, and these events are not, you don't have that many a day, so it's
right. Yes. Yes. This is what I mean.
So that you can use because they are not, you don't have that many.
Right.
Date time was a big factor in the integration.
Yeah. So how sure you guys think that the data are the same? Is it probabilistic or?
Oh no, because they have the same observation, exactly like you have different sources. So all these instruments keep their own data.
Yes.
Okay, but they're observing the same event. Okay, so now you have to see. So these are, and what they're measuring can be different.
Yes.
But then so you want to say, well, these are from the same event, so that you can merge them and then see how you can use the data in more comprehensive data.
Right. Yeah. Okay.
So there are also some regions that are also in terms of the data that we also get here are active regions. So basically, there are some regions that are more active, and when you can have white sun when there is no activity. So when you have more these active regions are linked to the flares. So we want to see how the activities on how the active region, what the link between the active region and the flares. So that was the type of study. So we were using here machine learning prediction. This line, this is what is the prediction by the physicist. And then what we use to predict, this is the average. What we use for prediction using machine learning and based on the correlation between the active regions, which are here, and the prediction, just by learning. So there is something there to be done, but yeah, if we still get some kind of activities there. So these are some SAP events. I'll come back to it. And in physics, they were classified into two. They have this Hale classifier, Macintosh classification, and so based on the properties, and we try to see, and that gives different type of flares of different type of category that we have there. Now, when we do prediction, you need more data, but this data is unbalanced. We don't have that many values there. You can have the ratio of white sun, where there is no activity, and where you have activity 1/34, or sometimes 1/55. Yes. So that's a big challenge. So we were trying to see if to do the prediction, if we can sample, but that can also lead to overfitting. Yes. As you know, or try to see how we can generate realistic data to just augment the data to try to do some prediction. And that was what we were trying to study here. Okay. So these are different cycles that we have there. So the solar cycle 24 was between 2010 and 2020. And we're trying to see if we can also use the cycle before, 97, 2009, and cycle 22 that was there. And we try to see if we can use one of these, the data to one cycle, to study it, do the machine learning, and see if we can use that to predict the other. So yes, that was a good idea, but because of the imbalance of data, it was not giving. So these are the type of so the flux that we get, same type of data that we have there, and we represent that. And so we try by just using sampling, oversampling, use other methods, but because we don't have enough data there, so it's not. When you oversample, all you do is overfitting, and it's not getting kind of result. So what we try to do is see how we can. But when we were, what we find out that when you learn on the solar cycle 24, you cannot use that to predict on the others because you have less data. 22 prediction is a bit better, but still, we need more data to be able to do something that can be of interest. So, these are just. So, when we talk about the solar flares and solar activities, these are that shows some of the characteristics, but I won't go into the physics details. I don't understand them, well myself. So I'm helping just with the data. But that gives you the type of a visualization of the type of data we are dealing with. Okay, so we were using the GOES satellite here to observe some flux emissions there. So you have that shows solar non-flares and flare activities there that we can overlap here. So where we have the flares is less than where we don't have flares. So that's again what I was talking about. So this is just but the classification. So they have the health classifiers, the classification of flares, and the Macintosh classification. This here shows the superimposition of these classes and see some properties. With some properties, you get better result, better prediction. But that is, that this is also the rate of prediction here. When we say best, it's 1 out of, so about 9%. So it's not that big, but because of the imbalance of data, that's what we can get here. Okay. The other thing that we're doing was to use some kind of ensemble here of, and then each of these are machine learning, neural networks. And each of them is using just a subset of the features and try to see if we can combine them here to do some kind of prediction. So that's also maybe that can give, but these are what we are looking at as well to be able to do that. Okay, and so I'll skip that one. So these are some other set of data that we want to be able to use. These are the soil data that we have there and some kind of properties that we are trying to observe. So basically, these are what we try to do in the data analytics there that we have. So if I can summarize what we did first was we have a different data set from different sources that we try to integrate. So create a database, try to integrate this database there. Then second, try to use that to do prediction. So one thing we were doing also, and then we were stuck, keeping the data there, and that takes time. So we want to be able to reduce for some of these events. We were trying to do some kind of data feature reduction using the autoencoders. But now we want to use machine learning to be able to do some prediction based on data. So I can show you some examples there more, but these are the same type of ideas, and we can fit in some kind of regression line. So try to see if we have anything that can work better. But yeah, so we try to develop the SLP3 database that we have there that we talk about. We try to do some prediction there. We still have a lot to do because of the data and balance. So what we're looking at are ways of producing some more realistic data. Maybe that will help. And we are now extending that to historical data and then trying to see if we can get better results. Okay, thank you for your attention.
Any questions?
So thank you for a nice talk. Oh, okay. Thanks a lot for the nice talk again. So.
Okay, so if you say so, you are a physicist. So
No,
if you say so, then thank you.
No.
Yes.
Be ready. No. I did some work in 2014 when I was in Switzerland working with Professor Herman there. And we were interested in analyzing the solar flares in terms of statistical properties. And the idea was that we wanted, of course, as physicists, we wanted to use magnetohydrodynamics model and try to understand how the magnetic fields of flux tubes were twisting. And we are mostly interested in the photosphere. As you said, there are these three different layers. And the main important thing for us at that moment was to show that there was some sort of intermittency in the transient behavior of the system, and how this transient was displaying itself in terms of instance of distribution of energy of the solar flares itself. When the magnetic flux tube twists, it releases energy. So this is what you were showing, those black spots.
Yeah.
And we wanted to know the energy of that black spot, how do they distribute statistically, and what is the intertime distribution between them. So these were our main questions at that particular moment. And we found very, very nice power laws. At that time, we used GOES and BATSI. BATSI?
Yes.
Yes. Okay. Yes. Databases. And we found power laws everywhere. So when you find power laws everywhere, I mean, distribution which is not Gaussian, which has a long tail in terms of power law exponent. And we could compare our model with the power laws which were being displayed from the databases. And these are very common things in terms, I mean, not very common, but you could see things similar in stock market and earthquakes.
Yes.
So this was implying, our idea was at that time, sorry to describe
no,
the model,
that's
but
fine.
this
That's,
I'm going to some point.
No, that's good. That's
so
good.
our idea was to show that there was some sort of self-organized criticality inside of that system. So that would be a system which organizes itself and from time to time releases powers, energy that is not really predictable. Why? Because of these long tails, rare events like earthquakes, they exist. And we know for a fact that they exist. And it could be the same in the solar flare. So I wonder if you were also interested in these types of statistical distributions, and if you had computed some of them as well, because you have now a huge database and up to date, especially from GOES, as I see you're still working, you have data from 2020.
So yes, so that's good, and I'm sure my physics colleagues are interested in that. So for us, they tell us which data to use. So I'm not into the physics, but as I said, what we try to use is not only just pure machine learning, but if we can use this kind of statistical previous study and see how we can combine that with machine learning, or even use that to define the loss function in the learning, that can be useful.
So these are things that are being used now. Some sort of hybridization between
so that was a bit what I tried to say in here. So that was what you described was the physics-based modeling, and we try to use also just data driven, but what we try to do is just combine these two there and see what the best way is.
What your group
that's what we try to focus on now.
So is it easy to work with physicists, or how
you have to
tolerance, no, a lot of tolerance.
Well, that wasn't big of the main issue. Well, okay, so first of all, even the jargon that we're using, I was not, so I have to, for me to understand what they are saying, Yes. But then the main problem was the publications.
Oh, I see.
Okay, in computer science, you write the full paper, even for a conference. So the physics conference, you basically need to raise your hand and you can give a talk, right? So, well, you send an abstract, so it's not a full paper, it's there. So then you can have that. So when we say we want to publish to a conference, they said no. We don't. They said, but our conferences are sometimes more difficult to get in. I know. Then, so, but, that was, so most of these papers were public for publish in physics venue.
Okay. So but this is the type of approach that you are using.
Yeah.
Hybrid.
Yeah, hybrid. Yes,
Very nice.
and then have to use that.
Very
combine
powerful.
them.
Must be very.
Yeah.
Thank you very much.
Welcome.
I have a technical question and
a technical comment.
And a technical comment.
Yes.
Technical comment is, I know you well for over 30 years, and I remember you used to work on spatial databases.
Yes.
What's related to images, to geographic objects, and I see many images there. And I always thought about you. I remember we discussing at that time, like, what are these known spatial databases systems that are appropriate to deal with images, to moving images and everything else. So first question is, have you been going back to some of the established foundations of spatial databases that could help you somehow dealing with the integration, for example, data, and also to support some machine learning applications? The second question, just a quick one, is easier, is, okay, you get 50 terabytes a day?
Yes.
Where is all this data?
Yes. So they have that is one problem, and so for this type of so maybe I can start by the second question there. When they told me the number of data coming, so I said maybe we need to summarize the data, but they said no, you don't want, we want everything. So you cannot even say you want to reduce the data, because they want to be able to have access to data when they want it. So we are not doing anything just to even summarize the data. So we're integrating the entire data set there, but something has to be done with it. And I think the way to do it is, if we can extract whatever we need from it, if we know what we need from this data, and keep that there, and the rest maybe put on tape, that would tape, so that we can still go back to the tape and get it. But that's, what we can do. Now, going back to when we started as, yeah.
Okay, all these tapes is what? NASA? You have access?
No, these are pop. Yeah. We did that. So, but we get that, and then we store it at NASA. So we got the funding for this study, part from NSF, plus from NASA. Yeah. No structure. We created the structure, like the database schema, to be able to represent it. So now, as you summarize it, I started by looking at spatial databases. Then, so for me, I'm doing the same thing. And I went from there. I'm also part of the multimedia community, because images are data in high dimensional spaces. And so when you do by search of, so you use that. So I'm part of the multimedia community as well. But here you have that. And then, so currently, we have not even tried to use the images themselves. And so we have different sources of data, and how to merge all of them to do the learning. So we're just, started. What we try to do is just, we're scratching the surface of the problem, because you have different type of data, how to do multimodal learning. So that will be maybe more effective, but also more challenging.
More questions? Oh, all righty, thank you.
Okay. So we try to keep it within an hour, so it's good.
It's all right. Okay. So,